Good evening, all of you. Today we are going to see an important topic, that is notch filter design. As a special case, we are going to see about the basic 20 notch filter design. Before going into that, we must know what is band elimination filter or band stop filter. So this is, in the x-axis we take frequency, and in the y-axis we take voltage gain. So the band elimination filter or band stop filter, BSF means band stop filter, which it does not allow the frequencies ranging from F1 to F2. That is totally eliminated. That means right from DC, that is 0 to F1 it allows. F1 to F2 it won't allow, and from F2 to infinity, basically theory wise to infinity, it allows all other frequencies. So this is the basic band elimination filter, or otherwise called as band stop filter. So to model this circuit diagram, we take a simple configuration of low pass filter and high pass filter, and then giving to the amplifier and getting the amplified output. So our idea is a range of frequencies is not allowed, all other frequencies are allowed. But in the case of notch filter, it will, for ideal case, it will not allow a single frequency. For example, supply line frequency 50 hertz. That noise has to be suppressed. In that case and all, we must go for notch filter. So notch filter is a special case of band elimination filter. No doubt about it. Okay. So where are the interruptions? Suppose one particular frequency, but eliminating a particular frequency in the real time or in the practical case is very difficult. So we can call it as a narrow band of frequencies. So those narrow band of frequencies should be eliminated. So such kind of filter is called notch filter. But what is the ideal case? Ideal case, only one frequency has to be eliminated. That is the ideal case. Okay, we will go into the basics now. So to realize this band stop filter or band elimination filter, we have low pass filter and high pass filter. The signal input is given to both the low pass and high pass, and then this signal is amplified and you will get the output. Similarly, high pass filter output, it gets amplified. Now how to fix the cutoff frequencies for low pass? So you all know that low pass frequencies right from DC to some frequency it allows. Say for example, F1 is 1 kilohertz, means this circuit will allow from 0 to 1 kilohertz. Now if you make this as 10 kilohertz, so high pass frequency cutoff frequency is set to 10 kilohertz. That means 10 kilohertz, and anything above that will be conducted by high pass frequency. So in between this 1 to 10 kilohertz, those frequencies are not allowed by either by low pass filter or by high pass filter. So those frequencies are suppressed. When this bandwidth is very narrow, then we call it as notch filter. Okay, now this is the idea. So low pass filter, you all know that R and C. So here we have this T section R and C. So you all know that capacitance for high frequency, you can visualize the capacitance as a short circuit. So just if you see, if high frequency tries to go through this 2R, it is grounded. But whereas the same input goes to this section also, it's a high pass filter. So this is capacitance is connected in series. So all the high frequencies are allowed, but low frequencies is rejected. Because you all know that Xc is equal to 1 by 2 pi Fc, capacitive reactance. So when frequencies goes up, reactance, that is resistance suffered by the capacitance, comes down. So that's the idea. So low frequencies are allowed by this circuit, and high frequencies are allowed by the parallel circuit. So that's why this is one T network, this is another T network, both are in parallel. So this is called as twin T network. So ideally this is used to notch the unwanted frequency. So the notch frequency is given by 1 by 4 pi RC. I already told you it is only one frequency, but a very narrow bandwidth is there for the practical case. So what my design idea is, always fix the value for C, because you don't have a wide range of capacitance. First you fix the required frequency that has to be not, that has to be removed or that should not be allowed to the next stage. Then fix the value of C. Now the only unknown parameter is R. From this you find the R and then substitute the value of R, that component value. If this is 2R means R into 2, that value you connect it here. If you do that, for example, if Fn I am getting it as 1 kilohertz, that 1 kilohertz is not allowed by this circuit. It is rejected. All other frequencies goes to the output. So here you will be having a range of frequencies, but 1 kilohertz is suppressed. You can design for 10 kilohertz, 50 hertz, like that. The unwanted, you want to suppress certain frequency, you can always get the help from notch filter design. Okay, so all the frequencies are bombarded into this 20 circuit. Basically it is a passive circuit. So this passes through the circuit and goes to the output. So the unwanted frequency is removed, say 1 kilohertz, or if you design for 10 kilohertz, mean 10 kilohertz is rejected by the circuit. The signal may be very weak here, then you can go for amplification. For that you can get the help from operational amplifier, where you get a very big gain. And of course you should look into the data sheet so that it supports that amount of bandwidth that is pumped into the circuit. So here you can if you can connect operational amplifier or unity gain. Initially if you want to isolate, you can go for unity gain. So this is plus minus, you can connect it here, unity gain amplifier, then output, and then you can subsequent stages you can go for amplification with the same operational amplifier. Okay, so that's the idea. Now if you see, this is low pass filter, this is high pass filter. If you compare with the basic diagram, low pass filter, high pass, but the signal is given to both the circuits. And finally the amplifier section is missing, so first I will put an isolator. Isolator means this, you all know that our operational amplifier input impedance for the ideal case is infinity, whereas the output impedance is lower. Therefore the two stages are very well isolated. So this signal gets coupled into the next stage. There you put a high gain amplifier using the same operational amplifier itself, so you will get a very good amplification. So the notch frequency is given by 1 by 4 pi RC. I already told you. Fix the frequency that has to be eliminated, fix the value of capacitor, and solving this equation you will get the required resistance value. That can be easily, we can get the component, no problem at all. So that's all about basic 20 notch filter design. Where it is used in so many areas, in so many applications, RF applications, certain frequencies give, when it enters to the certain, that signal is also amplified. So you want to remove the unwanted frequencies, especially single frequency, which gives a huge trouble. So in that case, this notch filter circuit is very, very useful. For example, simple examples is, if India means it is 50 hertz, in US means it's 60 hertz. This is all supply line noise. You will be getting a motorboating sound like that. So to eliminate this 50 hertz or 60 hertz, you can design a notch filter that is centered around 50 hertz and 60 hertz. But one important problem you must note down, when you, the signal itself can contain 50 hertz and 60 hertz. So in that case you cannot put a notch filter, because if you are interested in amplifying the signal of 50 hertz and 60 hertz, then if you put a notch filter, what will happen? The signal of 50 hertz and 60 hertz will die. So you have to see, based on the application, what are the frequencies that be allowed or should be rejected. So for a very narrow band of frequency that has to be eliminated, you always go for notch filter. So this, without the operational amplifier, it is a passive. When you connect an operational amplifier and subsequent stages where you use semiconductors and other ICs, then it becomes active. Hope you have understood this topic on notch filter. Thanks for watching this video. Nandri.